actually don't think I've been out here since the first meeting.
Let me minimize it. Okay. Let's do this. Oh gosh, this is so small. What the heck? Just show us. How do I do that? Do that one. Okay.
I think you can just go to another page and it'll just go into the minimized screen.
Oops. Alrighty, howdy y'all. So this is our last meeting for this fall. And first off, we're actually going to introduce Jonathan Stine. He's going to be doing a presentation on using magnetic fabrics to quantify the deformation of the Onion Creek Salt Shoulder Paradox Basin, Utah. That's a lot of words. Yeah, he's a lovely PhD candidate here, and he works in the paleomagnetism lab. So give a round of applause to John.
Oh, you don't want to do the
No, it goes by.
Oh, you just-
So like, yeah, we make a talk.
All right.
And we get your stuff after. What's up?
What is a magnetic fabric?
I'll go over that in the presentation. Yeah. Be a long presentation.
Oh, yeah.
Oh,
Go
right.
look. It's on.
This is gonna be a little more
It's
jolly.
on
Oh,
camera.
sorry.
I didn't realize it was on. That would be funny.
Oh, I
Yeah.
yeah.
Me too. That's why I didn't realize it was on.
Yeah.
Because you usually have to do that very SOC.
All right.
Pizza
So,
gets cold.
so they're doing the share screen. So,
That's the compromise we've made.
so they're doing the share screen so people at Zoom can see it.
Yes.
Good. Okay.
I don't know if it's set on sharing that screen yet.
The rogues gallery over there.
That is a good idea, John. The things I basically.
It's
Yeah, it's on share screen.
there you go. Yeah, it's usually.
Yeah. There we go.
Easily impressed.
Well, thank you, everybody. Thanks for coming. So today I'm going to talk about part of my dissertation research. This is part actually what I'm going to present at AGU, I think next Thursday. And yeah, so I'm just padding it out. So you mentioned that you wanted about like half an hour presentation, right? Half an hour, 40 minutes. So I padded out with a lot more background to explain things like what are magnetic fabrics, what's a salt shoulder, et cetera, et cetera. So but as for going on, just wanted to give a shout out to my co-authors. So, you know, of course, my advisor, Dr. John Geisman, Sarah Giles, who's another PhD student at Columbia University. And then last but certainly not least, David Langford Bravo, who is a PhD student at UT El Paso. And David and I actually, we met up online because we both had similar research. We're both looking in the exact same area. And so just a cool like way of, I don't know, like collaboration, especially among younger people, is really, really cool. And he did a lot of the structural work, the mapping. He did like a 3D model, et cetera. And without any of that, like I would not have nearly as good of an interpretation of the data as without. So just want to give a shout out to him. All right, so let's go into actually what are salt tectonics first. So if you guys go out to the Gulf of Mexico, this is a recent bathymetry map of the Gulf of Mexico. You notice like all these like pop marks on it. Like it looks kind of weird compared to say if you're on the coast of like New York, et cetera. And if you're going to take this is an interpretation of a seismic section. If you're going to take like a cross section of the area based off seismic data, you'll notice that the sediments all deformed and we got like these big blobs of material here. And these big blobs are actually made up out of halite, all right? Made up of salts. And so that is salt tectonics. That's just kind of a brief introduction. Now we have to kind of go into a little bit of nitty gritty. So first of all, there's a difference between what a chemist calls salt and what a geologist calls salt. So a chemist would just define a salt simply as, you can correct me on this, would define it as just any kind of ionic bond, any compound that's ionically bonded that's electrically neutral, right? So based off that definition, like galena, lead sulfide would be a salt. Pyrite, iron sulfide would also be considered a salt. But in geology, we don't do that. In geology, we use salt essentially as a synonym, for evaporites. So whenever you hear a geologist say salt, they're referring to usually 3 out of these 4 minerals: halite, sodium chloride, gypsum, calcium sulfite, and water, and hydrite, calcium sulfite, and then sylvite, potassium chloride. Okay. So how do we get salts? So basically all you have to do is you have to start off with a basin, so a large body of water, and you have to close off that basin so no new water is flooding in. Okay. So think of the Dead Sea. And when that happens, when no new water is flooding in, and if the climate is dry enough, potentially hot enough, you'll start evaporating the water and you'll be leaving these evaporite deposits of salt. Why does this happen? I don't know if anyone's taken petrology in this meeting right now. It's essentially fractional crystallization, very similar, probably even simpler than what occurs in a magma. So you have your solution, which is water. The water has, these sodium ions, these chloride ions, calcium, sulfur, etc. And as the water is leaving the solution, you're in turn super saturating it with other materials. And so these minerals have to precipitate out, similar to how, like, say, olivine precipitate out of a magma. And it occurs usually in a certain series, not unlike Bowen's reaction series. So believe it or not, actually the first mineral that we crystallize out would be calcite, followed by gypsum, then halite, and ending with sylvite. And if you just keep evaporating, eventually you'll have these large areas. Like this is, I don't know if I'm pronouncing it right, the Salar de Uyuni in Bolivia, where it's just basically the whole land is a salt. Like this used to be a lake, it got closed off, evaporated away, and then all you have are these salt deposits. But sedimentation occurs in cycles. So very often, if you have a large enough basin, like say like the Mediterranean Sea, it'll occur in these cycles where sometimes we have like the Strait of Gibraltar here, so the Atlantic Ocean's flowing in, so no evaporites will develop. But during the Miocene, due to there's debate exactly why it happened, but could have been tectonics, could have been climate. But for long story short, the Mediterranean was cut off from the Atlantic Ocean, began to evaporate. So you end up with these sequences within the Mediterranean of just regular siliciclastic sediments like a shale, and then evaporite layers composed of salt. Okay, and these are very common in a lot of basins. So in fact, if you look all over the world, you can see these are all basins that have a really large salt deposit. So like I said, here's the Mediterranean Sea, in between, the Persian Gulf. Forget what the name of this gulf is. Then of course you have the, the Red Sea, yeah, the Red Sea, thank you. And the Gulf of Mexico, and you'll have these salt deposits all over the world. Okay. Oh, and here's just another, just wanted to quickly go through, I'm saying these also occur during certain time periods, right? So you expect during supercontinents that you would have the conditions to form like a large basin in the middle of the continent that could be cut out, et cetera. We notice that there are certain correlations between these large evaporites at time. Okay, so why do we care? Why we have all these salt deposits? Who cares? Well, so salt, specifically halite, sodium chloride, is one of the few minerals that not only human beings can eat, but it's one of the few minerals that we have to eat in order to live. If you don't have enough sodium in your diet, you will have a seizure and eventually die. Now, of course, we get our salt naturally from like fruits and meats, et cetera, but there is something that is called salt hunger. So you do need it in order to live. And then, of course, for thousands of years, people have noticed that if you put salt on meat, the meat won't go bad. And that's just because the salt's sucking up all the water and the bacteria has no water to live off of, thus preventing the meat from molding. And the salt was very, very valuable to people for thousands of years. And I mean thousands. Like we have salt mines going back to like the Neolithic, before there was writing in Poland. And of course, there have been, like historically, not too long ago, there have been a lot of social upheaval due to like people taxing salt or depriving people of salt. So one of the big reasons for the French Revolution was that the king put a huge tax on salt. And if you like try to store it, they would tax you even more, and thus got the peasants really upset. And that was one of the reasons. And then of course, Gandhi's famous Salt March, where he basically refused to buy salt from the British, et cetera, and they made their own salt. So very important for history in general. For geology, especially for petroleum geology, salt's very important because it serves as a seal. So I don't know how familiar people here are with just basic petroleum geology, but let's just imagine we have our salt or our oil right over here, okay, in this reservoir. The oil wants to escape. Because the salt precipitates out, like it actually crystallizes, rather than being settled like any other like sandstone, that means that there's no porosity. It's just like one giant rock. So it serves very similar to like, say, almost like a basalt, and the oil's not going to go anywhere. So it makes an excellent seal for oil. So very early on, when oil was first being drilled for, that'd be one of the things people would look for when they were drilling these large salt layers, because usually they would have a good oil deposit right underneath it. Okay, so we have that. We've established what salt is. Now let's go into salt tectonics. So salt is very, very weak, and actually over geologic time, it will behave like a fluid. It will flow around, not unlike glaciers, okay? Because it kind of flows around, et cetera, you'll get a lot of deformation both within the salt and within the overlying sediments, okay? And these structures, you'll get anticlines, you'll get rift basins, et cetera, not unlike traditional tectonics, hence the name salt tectonics. It's not actually tectonics, but it's creating something kind of like it due to the movement of the salt. And here's just kind of like an example here. You know, if you didn't know the salt here, you would just imagine this as like, you know, any other typical fold or rifting, right? You would imagine like, oh, maybe the plate's being pulled apart, et cetera, but it's not, it's just the salt moving. And that's what's causing these fault blocks, these anticlines, et cetera. Okay, so why does this happen? So I'm just trying to move. Oops. Here, oh, there we go, thank you.
That'll disappear on your video if you're talking.
So, okay. So why does this happen? Why does salt behave this way? We've already said like it's mechanically weak, but why does it flow? Now, if you look on Wikipedia, and this is only just because people thought this is the way it operated for the longest time, people thought that this happened because of density, all right? So salt in general is a lot less dense than just your typical shale. So people thought that, all right, we have these salt layers, which are not very dense. We have, say, like basically any other rock on top of it. Well, then it must behave very similar to like a lava lamp, or if you just put oil and water, the salt wants to come back up and thus creates these structures, et cetera. And density inversion or density buoyancy, this kind of like, oh, this thing wants to float up, is definitely a driver of why salt tectonics, but it's not the main cause. All right, so essentially the salt will want to do this, but the salt needs a pathway in order to do this. So if the salt is just completely encased, it's not going to flow. And case in point, if you look at the Permian Basin in Texas, you have these huge evaporite layers on the Castile Formation, but really little to no diapirs there, okay? So then the theory was revised relatively recently, I want to say the past like 10 years or so, based off of physics models. And so essentially it comes down to is you don't think of salt anymore like oil and water. Think of it more like groundwater in an aquifer, okay? If there is different like pressure inversions, just like how water want to flow down to where there's lower pressure, like a hydraulic head, salt will want to do the exact same thing. And especially since sedimentation can be uneven, if you have like, say, like a really large accumulation of sediment right here, but maybe not so much over here, then the salt, because of density inversion, will flow that way, thus creating your salt structures. And then of course, I'm not going to get into this in the presentation because it gets overly complicated, but of course, if you do have a fault, like if your salt basin is in an area that's very tectonically active, that would create a pathway for the salt to form, you know, but that's a little too complicated. Okay, speaking of complicated, salt structures, like I said, because they're mechanically weak, because they flow like a glacier, their structure can get complicated very, very quickly. And some of the best places in the world to see this would be, is there a laser pointer here? Anything there? Well, it's okay. Some of the best places to see it would be right here in Iran. Right there, they have the Hormuz salt from the Persian Gulf that's getting pushed out because of the rifting over here. And thus it creates all these beautiful salt glaciers that are being pushed out to the surface. And yeah, so if you do get a chance to go down there, you can see these really, really beautiful structures. And you actually get to get on one of these tours. They're usually pretty sketchy, but if you're able to like get a local to get you on these tours, you can get like these really beautiful, like all these like different folds and recumbent folds, etc. Really complicated, but really beautiful. And just here's some more. You can see the, maybe I know these guys can see it up here. Just got the syncline, this recumbent fold right over here. Here's just a cross section of like a typical salt glacier. You can see all this always going on. You won't have to do this in structural geology, at least I don't think you do. Okay. And then, okay, so that's just how salt itself deforms. But salt also deforms the sediment it interacts with. All right. So, and it makes a kind of sense, right? So if the salt rises, okay, it'll serve as like a barrier for the sediment to accumulate, right? But not only that, not only will it kind of trap the sediment here, but also kind of the salt withdrawing will create a continued depot center for, so like there's more space for the sediment to come down there. So you can get these really large accumulations of sediment in between salt anticlines, and these are usually referred to as mini basins. These are usually very important in the petroleum industry. And here's just another kind of model showing off, like if you just kind of imagine, these are just referred to as salt walls or salt anticlines. Just imagine them as a basic cylindrical anticline. You can imagine these are tall enough in this like a fluvial system, then yeah, the sediments will probably only go down this pathway because it's too high to come over here. And then of course, the closer we get to the diapir, the sediments are going to get more and more deformed. And it's a very complicated dance between how fast the diapir is rising versus how fast the sediment's accumulating. So if the diapir is rising faster than the sediment can accumulate, then you're going to get this much more prominent monoclinal-like folds, which are referred to as hooks, because they kind of look like a hook. And then, of course, if the sediment is at least keeping up with the diapir, you'll still get like a fold, but be much more gentler. And these are usually referred to as a wedge. And was it coming out recently in the literature, I want to say the past 15, 20 years or so, they've actually created what they call halokinetic sequence stratigraphy. So it's essentially sequence stratigraphy, but you're basing it off of these various structures you can see here in the sediment. You can record like, oh, okay, in this portion, the diapir was always rising faster than the sediment. In this portion, the sediment was keeping up with it or maybe going a little bit faster. So that's halokinetic sequence stratigraphy. And then if the diapir continues to go even faster, things get really wonky. You get these things called mega flaps, which I've seen before. They're pretty wild. It's basically the strata is just completely overturned. It used to be flat and now it's going almost like 92 degrees now. And then we also get these structures called salt shoulders, which are kind of the focus of my research in the paradox basin, I'll go into in a little bit. Okay, so now we got that all right. Let's actually go into the actual area that I'm studying. So really the best place in the world to see salt structures is Iran. But in the United States, we do have a spot where you can see salt structures at the surface, okay? And that's in Utah in the Paradox Basin, right over here. It goes through most of Utah and a little part of Colorado. And in the Paradox Basin, we have these really large salt anticlines that are exposed and that researchers can go to actually study salt tectonics in person. And so what we're focusing on is probably the best salt structure in the Paradox Basin, which is the Onion Creek Salt Diapir. So here's just a general bedrock map of the area where you can see the various sediments there, and you can see how the salt is affected at creating these really large anticlines. The Onion Creek Salt Diapir exposed, various faults. This is actually right near Arches National Park. Salt tectonics is one of the reasons why we have Arches National Park. It creates the faults, etc. Okay, here's just a generalized cross section. Oh, sorry. Is it locked? Oh, there we go. So here's just a generalized cross section of the area. You can see it's very similar to this model right over here. It's essentially like how they think the sedimentation occurred in the Paradox Basin is essentially this model. They think, okay, we have the uncompadre uplift provided the sediment. It created differential loading, which caused the diapirs to rise during sedimentation, creating all these basins and salt anticlines, etc. That's kind of like a basic overview of it. And here you can see it kind of in person. There's all the salt anticlines and all the various ways that the beds are folded. Okay. Oh, and then, sorry. And then just kind of in this cross section here, I wanted to point out, yes, you can see the salt structures, and it's kind of hard to see in this section here, but the Moab Valley salt wall is like slightly covered by sediment. So really the best place to see an actual salt diapir in person is the Onion Creek salt diapir exposed here. And here's a picture I took of the Onion Creek salt diapir. You can see all the nice folds going on. Here's us actually walking through it. There's David right there. Solomon, I don't know if Solomon's here right now. Yeah, I don't see him, but Solomon went out here to collect samples with me. Here's this example, just kind of zooming in on some of like the chevron folds going on within the salt. But that's the salt itself. What we're actually focused more on is actually how the salt has deformed the sediment nearby. So here is a much more detailed bedrock map of the Onion Creek salt diapir and the sediments nearby it. So this is part of David's work. He actually presented this map for his dissertation last week. And so for the longest time, this block right over here was just referred to as the Cutler. Okay, and the Cutler is a very large group. You might as well just say, oh, this is early Permian sediments. And although when you go away from the Onion Creek salt diapir, you can split the Cutler into various members that are much more recognizable and much better dated. You couldn't really do that for this section here, which was very challenging because, or very frustrating because that meant like you couldn't really establish a time series with any of this stuff. So what David did was that he made a very detailed stratigraphic map of the entire area. And unfortunately, the only thing he could do was based off of thickness. But having said that, based off of thickness, he was able to tentatively correlate 14 different units that he mapped to the various members. So units 1 through 10 are correlated to the lower Cutler beds, which if proves to be true would make them about Permo-Pennsylvanian. And then units 11 through 13, and then part of the last unit, unit 14, are part of the Cedar Mesa Sandstone, which would make them about early Permian. And the uppermost part of the unit 14 be correlated to Oregon Rock Formation, which would make it somewhere between 290, 270 million years ago. Okay, so that's one of the parts that David did. So that's just kind of the basic stratigraphy of the area. And I just want to kind of show you just a really brief cross section of the area itself. So generally speaking, if you're just going to be very general about this area, you just describe it as a simple salt anticline. And that's what this cross section is showing here. This is from Dowling 2002. You can see just kind of very simple anticline. You can even see it, or sorry, I guess it's kind of hard to see the strike and dip symbols here, but if you kind of just look at strike and dip on these like larger cliff walls, yeah, it would just be kind of gently dipping like that. However, as you can see when you look in this map, when you kind of get closer to this area, things get a lot more deformed very, very quickly. So it's kind of showing just me kind of near the area. We can see this little tiny anticline coming up right near there. Here's another anticline closer to the diapir. Here's one of the larger anticlines that I don't know if you guys can see it very well on this. You can see it if you look at that TV over there a little bit better. The much larger outer anticlinal hinge that he called it. And so what this structure is, this whole like this really deformed area shown here is specifically called a salt shoulder. So why is it called a salt shoulder? So essentially what happens if you kind of imagine the diapir kind of going up the diapir, if the diapir kind of abruptly goes inward, creating like this little neck, then that's a salt shoulder. You can see if you kind of imagine the salt diapir as like the outline of a person, you can see like, okay, how this is the shoulder. And salt shoulders are becoming a lot more important because previously, if you were like a seismic geophysicist, you wouldn't be able to see this at all. This would be kind of combined with the salt. And they probably wouldn't even attempt drilling there. But now with better and better higher resolution seismic imaging, petroleum companies can actually see these structures, and they're proven to be really good plays, really good targets for petroleum exploration. Not to mention that they're also really potentially good plays for carbon storage, potentially storage for nuclear waste, et cetera. So these are becoming more and more important in the field of salt tectonics. But having said that, they're not very well understood. Hence why you need to do not only the detailed mapping that David did, but you need to do much more detailed structural analysis, which can be done by studying magnetic fabrics or the anisotropy of magnetic susceptibility. So what is anisotropy of magnetic susceptibility? Long story short, when you have a magnetic field, you're generating a magnetic field, and you put something in that magnetic field, the magnetic field will change. Okay. The reason why it does that is because when you put a magnet in a magnetic field, that magnet will become more magnetic, and they kind of combine together to create a much larger magnetic field. And that's, yeah, why it changes. And the property that causes that to happen, causes magnetic field to go up, is referred to as magnetic susceptibility. You know, how susceptible is it to a magnetic field? It's just a fancy way of saying how magnetic can it be if we put it into a magnetic field. And it's fairly easy to measure. Like I said, all you need to do is just need to generate a magnetic field, put a rock in there, see how it reacts, take the ratio of how the magnetic field changed to what the magnetic field used to be, and that's magnetic susceptibility. Okay. Just a simple property of rocks based off magnetics. But back around in the 1950s, a lot of researchers wondered what would happen if, because like I said, you just put the rock in the magnetic field. What would happen if you change the direction of like how you put the rock in the field? And so what we do, and what we do in the Paleomag lab, is that we take these rocks, we kind of cut them down to these like cylinders, and we put them in what's called a kappa bridge, that thing that generates magnetic field, and we put it in at a bunch of different directions. Okay. And if there is like a preference, if the specimen is more magnetic in a certain direction and not as others, that's referred to as anisotropy. Anisotropy is just a very fancy word just to say the thing is direction dependent. Okay. That's anisotropy. And the reason why this happens is because the magnetic minerals in the rock are oriented in a certain direction. All right. And that's what you're able to measure by seeing the anisotropy in the material. And the way the magnetic minerals are oriented is referred to as the magnetic fabric. Okay. Not unlike like a metamorphic fabric. Like, so you're looking through a schist and you see like how all the micas are aligned. Same exact concept. We're measuring the magnetic field. We're measuring the magnetic field of the rock. We see that they're all kind of oriented in a certain way. Hence, the magnetic minerals is oriented like that. Magnetic fabric. Okay. So you can do that. You can figure out how the minerals are oriented just by kind of spin them around in the kappa bridge. But you can also do something else, and that's basically you can figure out like how deformed is this fabric. And this is referred to as the anisotropy degree and the shape parameter. And it's essentially just taking a ratio of where the magnetic field is weakest and where it's strongest and where it's kind of like in between. You know, your K min, your K max, and your K intermediate. And you use that to figure out, all right, what's the shape? This is referred to as magnetic ellipsoid, or sorry, the anisotropy ellipsoid. What's the shape that this fabric is taking? Okay. Why do we care about that? And I believe you learn about this. I don't know, Marta's not here to ask. I believe you should learn about this in structure. But basically, if we're thinking of a sediment, okay, if the sediments are all kind of laid down, you know, it's this typical sedimentary process, then we'd imagine that the magnetic fabric should become like a pancake, right? Just be all kind of flat down. And that's referred to as oblate, all right? But if you add strain to it, pressure in a certain direction, then micas will begin to grow perpendicular to the strain direction, and thus the ellipsoid will kind of go from being a pancake to be more like a cigar, okay? It's just the same thing as like pencil fabric. And of course, you keep going, you're going to get more and more different features like cleavage, et cetera, until you get what's called triaxial, which is that all the magnetic directions are all pointing in different directions, et cetera. So we can use, and the science is still kind of fuzzy, because this, of course, can be caused by a lot of different things, but there's a lot of investigation like, okay, can we use these values, the shape parameter and the anisotropy degree, to actually quantify like, oh, how much strain was the rock being put under? Which would be a big deal, because we can actually say like, oh, you know, there's probably be be like, all right, we was going through like 1 million newtons of stress in this direction, et cetera, rather than just being like, oh, it was just stress in this direction. Okay. So we can do this. We can use the combination of like trying to infer how strained it is and what direction it's pointing to answer a lot of geologic problems. For example, if you're in a sedimentary area and all you see is shale, okay, there's no slate or anything like that, but there's some kind of orogeny nearby. The mountain is putting stress on the shale, but you can't see that, all right? The magnetic stability can't, because all the phyllosilicates are oriented in a direction, even if it's very weak, and they can pick it up and you can say like, okay, well, the strain of the mountain is going this far. You can do that. A lot of people do that to say, quantify how the Himalaya basin is being deformed. Other things you can do with it, kind of ignoring strain, is you can actually use it to figure out the flow of lavas. Right, you're just kind of looking at like a basaltic dike. Okay, yeah, you know it's going in maybe, or even so more complicated like a flood basalt. You're like, okay, it's all spread out, but what direction was it flowing in? All you see is just a black rock. All right, you could take a thin section, try to figure it out, but that takes a lot of time, takes a lot of money. With AMS, you could just drill a hole, put it in the machine, you can say, like, okay, it was going in that direction. Other things you can do is you can use it, say like, all right, so this was very weakly deformed right here. What if the thing is like, so this is a magmatite. What if the rock, the whole area was so deformed that we don't even know what the heck's going on? The AMS can help you kind of figure out like, okay, this is where the strain direction is going in. You can kind of get a better understanding of what is the geometry of the area. And this is really important for magmatites and also important for salt diapers and accompanying sediment. So kind of based on that, kind of knowing what AMS can do, I went out there and drilled at all these sites, approximately, what was it, 82, 85 sites. And site is just where I drilled, collecting somewhere between like 470, 500 specimens, and I measured them all. And you know, we use this drill, kind of go out there, collect it, measure it. All right. So before I just go into the AMS results, we have to understand what the magnetic mineralogy is. I'm not going to go too into much about how to calculate this because I feel like I'm giving enough background information already. But if you want, I can explain it later. Essentially, what happens is that you heat up like a small section of the sediment. You measure magnetic field, and you see at what temperature the magnetic field drops. You can use that to figure out what the mineral is. So in this case, a lot of them, pretty much all of them, drop at around 680 degrees, which tells you the magnetic mineral responsible for this is hematite. This is just, we kind of shock it with a really strong magnetic field and we see where it saturates, where it kind of flattens out. And based on where it flattens out, we can use that to figure out where the magnetic mineral is. This one, they all kind of saturate between 500 millitesla to about 1 Tesla, implying a combination of hematite and goethite. And then you can use inverse modeling to kind of see like, okay, what grains kind of fit, what grains can you kind of derive from this curve here? These are what's called unmixing curves. And you can use that to be like, all right, what population density is in here? And once again, it tells you mostly hematite. I'll explain this more later on. I kind of get back to the AMS results. And then finally, this hysteresis. So this is in a magnetic field. We measure, we kind of saturate the magnetic field up, reverse it, and kind of keep going back to where we started, and it creates this kind of S shape. And the important thing to keep in mind is that the hysteresis never flattens out. It should flatten out. And when it kind of keeps going on and on and on like that, that essentially tells you that, oh, there's a decent amount of micas in here that are causing this reaction. And then finally, when we look at thin sections, we can see, this was done by David. You can see that, yeah, there are a lot of biotites in there that he didn't orient the thin sections, but they look kind of oriented based off the pictures. And then, you also notice a lot of hematite coatings there, which agrees with a lot of my results. And then one final thing to keep in mind, this can be a caveat way at the end. He did infer that some of this hematite may be fluid-based rather than depositional. Some of it anyway. All right, now let's get back to the AMS results. All right, so we plot the shape parameter and the correct anisotropy, or sorry, the correct anisotropy, or sorry, shape parameter and correct anisotropy degree against to try to figure out, okay, what's the shape? And the vast majority of them all plot within the oblate range, okay, implying relatively minimal deformation, despite the fact that we saw all those folds, et cetera. But despite that, despite the fact that they're all kind of oblate, something was kind of noticed by both David, myself, and Sarah. I think Sarah was actually the one who noticed this, that when you actually look at the intensity of anisotropy degree and you put it on a map, you start noticing some interesting patterns. And the pattern was that if the sample was collected near an anticlinal hinge, the anisotropy degree was usually a little bit higher. And if it was located near a syncline, the anisotropy degree was usually a little bit lower. Okay. And once when David used his 3D model to create an isopac map, we noticed that not only were the specimens had higher anisotropy degree, located on an anticlinal hinge, but they were also, in terms of thickness, that's kind of hard to see on this paper, based off of thickness, the higher values were located on thinner areas, and the lower values, which were located on the synclines, were based in thicker areas. So why is this important? Well, this implies, well, one, the fact that it was all oblate implies that, okay, this is all syn depositional. That means that the rocks are being deformed while the salt is rising. The fact that they're all kind of like occurring within these various hinges tells you, like, all right, that the DIAPIR was kind of rising, creating these anticlines. That was kind of deforming the rocks, and where it was kind of dropping, it wasn't deforming it as much, and thus creating the lower anisotropy values. So that was just, excuse me, that was just the anisotropy degree. Then if we actually look, so that was just the intensity of the values, right? Now if we look at the actual directions, we plot them all up together. We notice that all the Kmin, Kmax, and intermediate values, they all plot along the bedding planes. Once again, implying that, okay, this is a syn depositional deformation. So this deformation is happening while the sediments are being deposited, not after they're lithified. And on a much larger scale, they're all roughly oriented northwest, southeast. So that kind of more or less agrees with, more or less agrees with that larger anticlinal structure. So it's just the magnetic foliation, which is essentially just kind of take the plane of which the K-min value kind of creates. And the important thing to know from this is that it agrees very well with the bedding plane. Once again, implying that we're seeing a syn depositional deformation. Like these things aren't really getting deformed after they're lithified. And then when we look at the magnetic lineations, we notice that on a larger scale, they seem to kind of follow these anticlines. But on a smaller scale, they follow the folds. And the really neat thing about this was that, so I collected this data while David was mapping it. Okay, so David made up these, found these fold axes independent of me identifying these lineations here. So what's really neat about this that you can kind of look at the lineation about the fold axis and figure out where the folds were. So kind of independent findings of the same result. Okay. So this is kind of like a little simplified model for you guys, kind of showing off everything that's been found so far. Is that, like I said before, so it's all kind of, all this is happening, the sediment is being deposited while the salt is rising. The salt that's deposited right on the top of these crests here, they're getting more deformed because the salt is kind of like inflating it. It's kind of pushing up on it, okay? That's why they're getting more deformed. The stuff that's being deposited in these depot centers, near these synclines, they're not getting deformed because they're not really getting anything pushed on them. They're still getting deformed when they're making a lineation, but their degree is lower because nothing's pushing on them. They're just kind of like, the salt is just kind of dropping, okay? So you can kind of see like, all right, where the salt was rising, where the salt was falling, kind of based off these values. And we can kind of infer, although I'd argue you need more data, thickness variations just by these values. So this is kind of summarizing that. So magnetic lineations are interpreted to kind of show the salt flow, evidence for the fact that it's syn depositional, the fact that it's primarily oblate ellipsoids with relatively lower values, and the kind of correlation between the lower values with the isopac map further supports the fact that it's all syn depositional deformation. So that's the presentation. Sorry it took so long. I know that was a lot, but yeah. So I wanted to, well, Serena's not here. I was going to thank her because she helped me prepare and measure a lot of those specimens. But a lot of other people over the years like Lachlan Vaughn, Jordan Newman, Julia Astramovich, Solomon, and of course my co-authors David, Sarah, and John Geisman. This is actually one here. We had to collect this stuff during the winter. So who was here during that? Chris, yeah, no. So there was no, that one was during the summer. There was I think it was not Leah's year. I think it was Takara's year. It was Takara's year where I went out in the winter and came back with this. But it was a fun time. And then thank you, of course, UTD for funding this, and AAPG for also funding this as well. All right, so with that being said, I know it was a lot. I know you guys are really tired and you just want pizza, but do you guys have any questions at all? Oh, thanks. Yeah.
First of all, I'd like to say thank you.
Thank you.
And also, I'm thinking of various applications of this. I imagine like one important application would be like for those mining salts, right?
Right.
Like to find out where the most salt would be possible, or
that's a. Oh, so you mean like in the sediment to figure out like, okay, where the salt?
where should I drill? So,
That could be an application. That's an interesting idea. But I think that probably a cheaper way would be that you just do seismic to kind of like get like a mapping of the area. But still, that's maybe a good way to figure out where the salt used to be. If the salt withdrawal would be interesting. That's actually an interesting application. I'll think about that.
Yeah, and also like what are maybe some of the most or one of the most important applications of figuring out like of the convolutions, I guess figuring out where the deformation is and everything, I guess will be the most.
So other than kind of understanding the geometry a lot better, so that when you're kind of you can use this as like, say, like an analog model to, for people when they're drilling on the Gulf of Mexico and they see this and they can't really imagine like, okay, where the air is going to be more deformed, they can use this to kind of guide them. Another important application, which will require more data and more time, that I really wanted to pursue would be, okay, can we use this to figure out permeability and porosity? So could we see like, based off of this, would like, say if there was oil or if you're using carbon sequestration trying to store it, could these values tell you like, all right, where what would be the best place to like store? Where would the oil most likely flow based off these values? But that would require a lot more data. And like you can see here, like I kind of missed this portion here, and I just need more time to come back there. But yeah, but that would be, I think, at least what I thought that'd be like the most important application, potential application, if it worked out.
Jordan also raised a hand, and I'm gonna raise the
Oh,
volume,
where? Oh,
just so we can like hear what he has to say.
how do I do that?
You'll have
Yeah.
to escape and do it this way.
Okay.
Jordan, if you want to ask your question, we'll see if we can hear you.
Sure. Can you hear me?
Yes.
So, John, has anyone calculated or figured out volumetrically how much salt is being extruded at what rate?
At the Onion Creek Salt DIAPIR?
Yeah.
No, not yet, believe it or not. They have for Arches National Park, but they haven't done it for the Onion Creek Salt DIAPIR. So that was one thing that David was trying to get money for, was to be like maybe hire or get like a master's student to like look at like satellite data to measure that. But no, not yet, unfortunately.
Cool. Thanks.
You're welcome. And thank you for, did I acknowledge you in the? Yes, I did. Okay, yes, because Jordan helped me. Because Jordan helped me sample this. Actually, he was one who took this picture. I actually collected probably the most with Jordan. He's the one who actually took this picture here. It's a good time. What's up?
So the lineation, can it be fairly flow direction instead of the how do you?
So the paleo flow direction kind of went in the opposite direction of it. So I originally thought that like, oh, could it be that as well? Because I was using the same logic of, oh, if it was perpendicular to it, then that would follow it. But at least my readings of paleo flow direction papers is that the micas would be oriented in this direction, 90 degrees away from it, and thus the AMS would be different from what I showed. So that's why I think it's more the salt. An interesting question though that I wasn't able to talk about here, which is why I need better age control, is it possible that this strain is from the ancestral Rockies rather than the salt? And if, oh, no, it's okay. And if like say all this stuff ends up being like Pennsylvanian, then that would have been during when the ancestral Rockies were, or sorry, if they end up being Pennsylvanian, that's when the Rockies are all rising. And thus that adds like kind of like a wrench into it because that would theoretically exert strain on it, but I didn't have enough time to talk about that. Hopefully, yeah.
Mean could be like they have parallel shortening.
Sorry?
Like K-mean value, it's all are perpendicular.
Yeah. So they're all,
Yes.
yeah. And then that's a weird thing too, like the uncompadre uplift and the salt DIAPIR are oriented in the exact same direction. So a lot of people think that that's actually one of the reasons why the DIAPIR rose was because it's kind of creating these fault blocks and that pushes them up. But that there's still a lot of debate on, yeah. I would really, the best way to answer that is I need to know how old they are. Because if it's a little bit more Pennsylvanian, early Permian, then by that point the ancestral Rockies weren't active anymore. They're kind of eroding away. So it would have to be only the salts. If it ends up being older than that, then I have to consider that as well. So, yeah. But no, really good question. Really good question. Because I thought about that paleo flow thing as well. Any others? Well, thank you very much for when we talk about this. I'll be part of my dissertation, so I might just use some of these slides for that. So thanks for being a good test audience for that. Thank you.
Thank you so much, Jonathan, for presenting on behalf of all the officers, even the ones who are not here. So back into our stuff. Like, yep, this guy. So, so every time we're going to talk about this, register for GeoClub. I'm not going to get too much into it, but again, you have to be registered so you get the proper paperwork to y'all for going on trips and such as this Arkansas trip coming up. So scholarship opportunities. So because a lot of these are not going to expire till, next June or such, they will be coming up again. But we have the Max Scoring Scholarship, which, again, apply to some of these if you can, because free money is always a good thing, especially when we're paying like $7,000 of tuition each semester. Yeah, and field camp and all that sort of stuff. There will be special scholarships coming out for those next semester. That does genuinely really help with affording field camp because you want to go on those trips. Those trips are important, and yeah, I'm not going to talk too much about that. But also there is the American Geosciences Institute. They're doing a geoscience profession scholarship, and that's $5,000. That's a lot of money. So that's due. Sorry, that is due February 13th in 2022. So that's going to be coming up, a couple months. So please get those in. We also have an internship opportunity and a couple scholarships listed on here. So we have the East Texas Geological Society Scholarship, which you can see all the requirements here. And if y'all are interested in some of these scholarships, we can always, we try to post this information as well. And if you can't find it, just contact us and we'll get this stuff to you. There's also the I cannot talk today. Natural Gas Society of East Texas Scholarship, which again is, free money. We like that. So going on to internships, Reed Engineering is seeking a geology student for part-time entry-level geotechnical logging positions. So internships are always a great thing to add to resumes, as well as it proves that you're actually trying to be a professional and gets you experience in the field. So there's also a couple other companies that are looking for paid geotechnical internships as well, including ECS Limited Geotechnical Soils Lab internship in Carrollton, Bryant Consultants, which is geotechnical engineering internships also in Carrollton, and Dynamic Engineering Consultants, my bad. So geotechnical internships in Allen, Texas, which is north of here. y'all are not familiar. So on to our Arkansas trip. So we still have 2 spots open. If you are interested, please contact us immediately so we get y'all's paperwork filed and submitted, because we're gonna get that submitted upcoming pretty soon. It is going,
Monday.
yeah, it's got to be submitted Monday, so very soon. Yeah, that's going to be December 17th through 19th, and we already have a group put together that talks about the itinerary of us going through the Ron Coleman mine, and it adds a lot of time for us to just explore like the town out there too. And there's a bunch of cool things out there, including some museums and such, and some hiking, all that sort of fun stuff. So also, I'll let Blake handle this one.
This is the last day for the blowout sale. We have a couple more things out there. A lot of stuff has had the price dropped on it, and yeah, just come down, check out what we have. It's pretty cool sale.
And last but not least, their socials. I know this one's kind of hammered into y'all by now, but we just like to provide it at every meeting just in case someone doesn't have it still. So as I talked about previously, the Facebook is good for alumni connections. And also there's a lot of people who post internships on there that are outside of UTD for, you know, companies that are looking for, as well as we post a lot of flyers and information on our Instagram. But the best way really to contact us and to like be in contact with people who are currently at UTD is in our group meet. And then you can ask the simple questions that might not necessarily apply, of like, hey, who has tent poles because I can't find mine, and all that sort of stuff. So, all right, but that's kind of it for our meeting. So if everyone wants to get signed in so we can do the door prize, go up and get some pizza, then we're good to go.
No, I just like it.
Oh, yeah, I've got a.
Yeah, I wanted to. Like, yeah, but the reason being, because it is a long.
I didn't spend enough time with
Over to yours. I'm gonna be in the audience section.
Yeah, I know, I've got calculus coming up. And then
So I
I've got
was worried
the
for
physics. Yeah, like, oh, shoot, 20. Yeah, it's almost like a, I don't know if like a dissertation is yeah, it's like 20 pages is, okay. Yeah,
There's like.
okay, you said I can just write the paper. So based off of like, basically do research on that area. Okay, can you send me again, just as a reminder in the email, just the description? All right, oops. Okay, that's a lot more relief because I thought these two projects, since they were like pretty big difference, that they would be a huge chunk, right? Thank you. That's a lot less stress. Okay.
All right, is everyone signed in at the front over here so we can do mineral profile? John, one. John, one.
They'll be around here.
Yeah, it's not that long though. But it's just not the same.
So is that everyone?
Yep.
All right.
So for the mineral door prize is number 12, Zerl. Zerl. Yeah. All right, thank you all everyone for coming. I'll let y'all eat your pizza, but we're gonna end here. Zerl. Bye, y'all. No.